welcome everybody, or maybe welcome back to most of you who attended the morning session already. Now we're even further in the schedule. That's really the end of the conference. And I announced already this morning that we are in a kind of synthesis mode, trying to bring together many of the elements that we have heard throughout the 3 days. You see that we have a quite broad topic, sustainable land use within SDGs and planetary boundaries. It's broad and encompassing. Still, we brought a bit of structure into this theme in the morning, and I just very briefly repeat that for you to organize your thinking a little bit. So we want to address the different demands that exist on land. And for that, we want to look at different sustainability criteria, environmental, economic, and social sustainability criteria, what kind of indicators we can come up for these criteria, what kind of interventions or solutions are we looking at, and also what can science, land system science, contribute, what kind of methods, what kind of tools, ranging all the way from models, scenarios, remote sensing, data approaches, big data approaches, case studies, and others to make this happen, to address this broad question what sustainable land use really is, across sectors, across scales, and also across regions. We will have time in the end to synthesize a bit. The first talk that's announced does not happen. Patrick Keyes from the US couldn't make it, and he didn't really like us to present him. So we'll start with Patrick Hostert's talk, which goes right into the matter of planetary boundaries. Benjamin will take time, will be strict on timing, so please stick to the 10 minutes that you have for the full presentations and the 3 minutes for the flash talks. Then we'll allow a few questions, 1 or 2 questions for each talk, and that should give us time to reflect on the items that I mentioned or others that you wish to raise on all these presentations.
Yeah, thanks a lot for having me. Happy to talk about planetary boundaries in terms of land. Then again, starting with, I'm not sure if there's really a land planetary boundary. Nevertheless, that's probably part of the discussion that we will have. We'd like to give credits to the co-authors, especially the team from Humboldt University on the one hand, but there are also quite a few people from the Potsdam Institute for Climate Impact Research at PIC. So let's delve into it directly. You are all aware, and I don't need to tell you about the land systems planetary boundary being part of the planetary boundary concept towards tipping points in the Earth system. There was a change, obviously, that not everybody was aware of between 2009 and 2015 publications, where there was a switch from having that boundary defined in terms of agriculture towards having that boundary defined in terms of forests. So, and that goes along also with a switch from this traffic light system from green to yellow. So there's some uncertainty already by definition in the system. I will stick now to what we had defined in 2015 by Steffen and others. So I will stick to the forest boundary for the moment, and we will have a discussion hopefully later on how much sense that makes and how to open that up. So what I would like to show here is how to quantify, in my opinion, the forest baseline and the change trajectories relate to that. So not a static boundary, but a boundary that relates to change, and the means of doing that is remote sensing. So the question here is, what is the deforestation trajectory? And we would like to do that not at a very broad global level, but we would like to do it at an ecoregion level. So that makes a difference here. So that's what you all know. That's the planetary boundary land definition as we see it by Steffen and others in 2015. Not going into detail here, but just to remind you, it's broad on 3 biome levels with different thresholds related to these biomes. Basically, it's the tropical, the temperate, and the boreal. While we don't stick to these 3 broad biomes, we stick to the definitions for the moment, which is of course open to discussion if those definitions make sense as thresholds. But instead of doing it based on 3 biomes, we look at the 846 ecoregions as presented by Olsen and others in 2001. There are other boundary definitions for ecoregions that could be similarly used. We use that one because it's quite comprehensive, and it also uses some compounds of the Earth system that are relevant, like, for example, mountainous regions and so on and so forth, so they show up here. And it enables something that the broad biome level boundaries don't enable, and that's a link not only to the climate system and climate change, but also to the biosphere integrity. And that's something that was highlighted in the 2015 paper as well. It's not just climate change that we focus upon with all the land boundaries in terms of tipping points. It's also biosphere integrity. So that's something we would like to enable here with our analysis. And we do that by linking it to state-of-the-art remote sensing. And this is, in this case, the Hansen data set, as we call it. So it's global forest and global forest change at a yearly basis, as it is provided by University of Maryland now since 2000 until, well, basically today, and it will be continue in the future. So what we have here is a 30-meter resolution global forest change data product. It's tree cover, so we can discuss definitions, of course, but basically that's the best that we have at the moment. So we want to compare that to the 846 ecoregions. If we look at that for the year 2000, you see that taking the same definitions as Steffen et al., you said a bit more of a contextualized picture here. It's not all green, yellow, and red, but all the regions have all of the system's trajectories here. What you also see, if you look carefully, is that some really important parts of global ecosystems are missing. So because of the forest definition, savannas and also the Mediterranean open forests are not in here. So that's probably also something you want to discuss, depending on what your target level is, if it is climate change tipping points or biosphere integrity related tipping points. If you look at the same for 2017, you see that all the trajectories are either neutral or negative. There's none positive. So if you look at those, about 350 to 400 ecoregions that are defined as forests, you find that there's quite some are stable, staying in the same definition criterion that they have been before between these 17 years, but you see that about 50 have changed. And some have changed directly from being safe to high risk. Quite a few, but some. And you see also that quite a few have changed from safe to increasing risk or from increasing risk to high risk. So I would like to focus on two of those because they have systemic means. One is Indonesia, simply because the 4 ones that skipped in 17 years across the increasing risk directly to a high risk all relate to Indonesia. And if we look in that, that's quite clear, so we all are aware of. So it's the palm oil plantations that kick in here, and where we see that even that this is tree cover, so from a climate perspective, that might be a different one as from the biosphere integrity perspective. There's quite a bit of change here in only 17 years. I'm also, I would like to caution that the Hansen data set doesn't cover it all. So it's rather a conservative estimate because also tree plantations are part of tree cover, of course. So it's just the change that we see here that makes it possible to tackle that in these 17 years of change analysis. And the second one I would like to focus upon, because much of the argument in the planetary boundaries definition is also taking from the example of the Amazon, because the Amazon has some systemic meaning in terms of global circulation, in terms of, for example, linking to the El Niño phenomenon, and to the hydrological global cycle. So Amazon is important here, and we see quite a few areas where we see from increasing risk going to high risk. And this is one of the studies that we did over the last years, where we looked into the arc of deforestation in Pará and Mato Grosso state in Brazil, where you can clearly see on a yearly basis how tree cover changed, how deforestation kicked in. And from that, you get a good handle on, for example, what is doing the change here. And differently from Indonesia, where you see the palm oil plantation being clearly in charge, here we see soy expansion and also grazing land expansion that are clearly linked to policies in Brazil. And with such yearly long-term maps, it's quite well possible to link what you map from remote sensing with what happens in terms of governance systems and policy on the ground. So that's quite nice way of looking into rather the fishbone patterns that you see here in the more remote north versus the very established early, so in orange colors, deforestation patterns, large scale, that we see here in Mato Grosso, for example, where soy is the major driver of change. it's really important to look at the drivers, because if you want to change something at the end of the day, getting a handle from looking into cover and use on the one hand, on the driver side on the other hand, I think that's the important thing. So if we look at, just for one example, this is South America, some of the ecoregions that we are looking at in forested ecosystems, you see here 2 or 3 things. First of all, they have different sizes, of course, so that's the bubble size. Secondly, we have looked at the trajectory from 2000 over 2009 to 2017, so you see 3 points here in time. This is 2000, 2009, 2017. You see the boundaries as defined by Stefan and others for the tropics in this case, between 65% and 83%. And you see that the trajectories have a very different meaning. So these static boundaries don't necessarily mean what we are looking for. So, for example, you have boundary transition here, but it's just a little extent of a little area. Then again, you have places like that, so which is in this case the Tocantins moist forest, where you see it's developing quite a bit along those 17 years. So deforestation is really a massive process here. And if we sum that up, there are also other regions, like if we look at the really large bubbles, so the Southwest Amazon moist forest, it's not developing a lot in change trajectory means, but as it is a huge area with lots of forest, it has quite a bit of a meaning if it changes. So, and the last thing I would like to mention, there are also different, well, say, trajectory speeds. So, for example, here you see it was between 2000 and 2009 rather dramatic, but then it slowed down between 2009 and 2017. We have quite the opposite here. So it was not as bad in terms of deforestation between 2000 and 2009, but for the Mato Grosso, we see that it sped up in the late 2010s. So there's a different meaning in that, and having a boundary defined in a more dynamic way and not in a static way, I think that's another important means of using remote sensing data. So are these things comparable? And if you look at the overall numbers, you would say, yeah, they are quite comparable. But if you break it down, you would say, no, not at all. So what we are talking here about is, it's really a sensitive thing depending on which data you use to analyze based on which parameters and variables and how you define them. So there's an intrinsic sensitivity to these analyses, and if you build assumptions on planetary boundaries, better be careful on what you use, and don't take the easy route and use the data that you are used to use, but use the best data you can. That's probably one of the take-home messages. So for discussion, I think the land system changes relate not only to climate change, as we all know, but they relate to biosphere integrity, to phosphorus and nitrogen inputs, to fresh water. So there are lots of things, and we need to think about the target variables. Depending on target variables, we might want to focus on forests one way or the other. And there are multiple land system changes at the ecoregion scale. So we need to capture these scale-wise differences to have the linkages between the different compounds of the Earth system and different potential tipping points. So methodologically, I think high-resolution change trajectories provide a different handle, a better entry point to really defining planetary boundaries. So for conclusions, for a next, say, set of planetary boundaries 3.0, if you want to call it that way, we should have more accurate and dynamic trajectories to get one step further in terms of measures for land system change. And that can be done with remote sensing at 10 to 30 meter or even finer resolutions for 30 or more years if you take the Landsat archive into account. And for the next step, maybe, we want to link that to the SDGs. So what does that mean for single properties of the SDG discussion and for the trade-offs in between? And my personal opinion is that the food system is the handle because it relates to all these sub-boundaries and tipping points that we are looking at in the land system. So if you get the food systems right, you probably get the land systems and planetary boundaries discussion right as well. Thank you for that.
Thank you very much. So Patrick gave us a nice introduction in the dynamics, specifically on the planetary boundaries. We have time for 1.5 questions. So is there other questions, please?
Thank you for the interesting talk. I think you're thinking mostly of boundaries in terms of area. We have seen in the first plenary session the intensity of use and the management of the area plays a very critical role. So it's a question and a suggestion that we should look at, or how you're thinking of looking at planetary boundaries that include the intensity.
Yeah, you see me nodding heavily. The reason for that is that, as I said, we want to stick here for the first step with the Steffen definition. Yeah, but I totally agree that in terms of land systems, we should not only look at the forestry system on the one hand, but agricultural systems are really important, especially when it comes to land use intensity issues. But also the forestry use intensity is something we should look at. And basically it's in the data as well. So now I showed yearly change maps, but now with weekly observations, basically, at least for many places in the world, we can go for phenology. So we can do that, what you suggest, and I would really support doing that.
Is there another short question and short answer, please? Okay.
Good point. Point taken.
Thanks. Okay, Patrick, thank you very much. So I welcome our next speaker, Mohammad from Deakin University, Australia.
Hi. Yeah. Good afternoon, everyone. My name is Mohammad Abdullah Shaikh, and I'm a part of Sustainable Research Lab at Deakin University, Australia. Today, I'll be talking about national land use performance based on downscaled planetary boundaries. In this research, we basically try to downscale the land system change planetary boundary and calculate the national level exceedances based on safe operating spaces of countries. Let's look at the life cycle of food system elements. So the life cycle stages of food system elements are cropland thirsty. Not just cropland thirsty, they are water thirsty. They emit a lot of carbon emissions as well. And with growing population, as the world is expecting to have about 9 billion people approximately by 2050 and more after that, the demand of food will increase, which in turn will put pressures on our global planetary boundaries. And for our focus, we are talking about land system change planetary boundaries specifically. Furthermore, the global teleconnections are complex. With flow of trade, with flow of food, the trade of food, a food is produced in a country, it's processed in another country, and is consumed in some other country, for example. So this complex global teleconnections and the land that is embodied with the flow of food and commodities gives rise to two more terminologies that we considered in this research. One is the consumption-based footprints. It's basically the indicator of allocating the responsibility to countries where consumption is happening. So for example, if a beef that was produced in Australia is consumed in Middle East, all the cropland impacts that occurred in Australia belong to Middle East because it's where it was consumed. On the other hand, there is another indicator called production-based footprints, and it's important to calculate because it's basically an indicator of the actual land footprints happening. So for example, the footprints happening at the actual place of production. So in this research, we considered these two indicators side by side for the first, not for the first time, but it's not heavily seen in the literature over a time series with respect to the planetary boundaries. So our major research objective is basically to operationalize the planetary boundary framework by calculating the national safe operating spaces and calculating country level exceedances based on their environmental cropland footprints. Our methodology basically considers, is divided into two steps. The thing you are seeing is the first step where we calculated the environmental cropland footprints of human food consumption. We use here a global multi-region input-output database called Axiobase. And the reason why we used multi-regional input-output database is because, as I said, we wanted to capture the global teleconnections of trade flows of food impacts, the land impacts associated with the food supply, food imports and exports. We wanted to capture the upstream and downstream impacts of supply chain, and we wanted to have a global image of, or a global result of the flow of land in between the whole life cycle of a food system. So essentially using the MRIO approach, we calculated national scale, direct and indirect consumption-based footprints, and direct and indirect production-based footprints. Alongside this, we took planetary boundary and we considered cropland as a planetary boundary. And then as we saw in the last talk, there is underpinning, there's substantial amount of debate on which boundary is right, which boundary is not right, but we feel that as we are talking about food systems and food system changes, cropland is is directly related to it, and that is why we considered the cropland planetary boundary in our research. So we basically downscaled the cropland planetary boundary using two alternatives. The first alternative is the fair share method. In this method, what we assumed is that cropland is a global resource. So every human on this planet has got equal right to that resource, no matter where they lie. So for example, if a small country like Luxembourg does not have enough land to produce, it does not mean that it does not have any share in the global planetary boundary. So in fair share allocation, we downscaled the planetary boundary based on country's population and allocated share to every country based on their population. The other alternative that we used is biophysical limits. So in this case, we downscale the planetary boundary based on the available cropland in that country. So for example, if a country like Australia has got massive amount of cropland, it should get higher share in the planetary boundary. Using these two approaches, in the end, we intended to calculate the consumption-based and production-based exceedances of countries. And if you note that the fair share allocation is pointing towards consumption-based exceedances because more people, more consumption. So they deserve more share in the planetary boundary. As far as biophysical limits are concerned, it's related to production-based. That means more land in the country means more share in the planetary boundary because that country has got responsibility to feed the rest of the world apart from its own requirements. So I'll jump onto the results. So our results basically comprise of a time series from 1995 to 2011, where we look at the country's perturbations against their allocated safe operating spaces. Overall, we cover the global study. This is a global study, so we have got 44 global economies and 5 rest of the world regions. And of course, we have got a matrix of exceedance matrix in the end, where we show a global outlook of how or which countries have perturbated or exceeded their safe operating spaces. Just to quickly give you a recap of how our results look like, this paper is still, the manuscript is still under preparation. So I'll just explain you how our results will look like. So on the axis, we have got cropland footprints. The units are millions square kilometers. On the x-axis, we have got years. The background colors you are seeing are the downscaled planetary boundary of a country. So this is China, and this is the consumption-based planetary boundary of a country. And the bars that you are looking at has got two colors. The blue color represents the direct impact of that country. That means the cropland that is coming from within China itself. And the white color you are looking at is the imported footprint of that country. That means the cropland, or the food that was imported in China and the cropland impacts that were associated with that food import in China. So if you look at the trend of China overall until 2011, the indirect impacts are increasing. And as we move forward, we have got interesting insights about our results and a lot of discussions that we will be taking part in. Alongside consumption, as I said, our analysis compares production-based footprints side by side with the consumption-based footprints. So similarly, we have got similar results for consumption-based and production-based footprints. So if you look at USA, for example, so a country like USA is already in its red zone and exceeding both of its consumption-based planetary boundary and production-based planetary boundary. We have got other examples as well, like a country like Japan, who does not have much of its cropland, is relying almost for all of its cropland needs on the other countries of the world. That means it's importing most of its cropland footprints from other countries of the world. Australia, which is considered to be the fruit basket of the world, has got like good impacts of export and exporting a lot of cropland to other countries of the world. So similarly, we've got lots of interesting insights coming up, and you will see a lot more of it in our paper that we intend to publish pretty soon. We also have such results like global exceedance matrix, a global outlook of which countries and how countries have performed over time, which countries are in the red zone, which countries are in the yellow zone, and which countries are in the red zone, and how those countries have performed. So for example, if you look at United Kingdom has moved from the yellow zone to the red zone, and we'll have like how red it is with time in the detailed paper. So I'll conclude by just saying that this kind of study is pretty important as far as the global agreements are concerned, as far as the Sustainable Development Goal 12, that is responsible consumption and responsible production is concerned. We have to look at it's more about food security and a fair share allocation of countries and giving space to countries which are underprivileged or which are still developing and giving them more space to develop. I hope I was able to explain you my research. Feel free to ask questions. Thank you.
Thank you, Mohammed. It was an interesting presentation where you combined the footprint methodology with the planetary boundary methodology. Do we have time for 2 questions? Holger, please. Patrick, sorry.
That's all right.
It's a running gag.
Interesting, thank you. Could you explain shortly how you downscaled the boundaries to the countries? Because we saw very different ones, of course, in red, green, and yellow.
So we downscaled based on 2 approaches. So our first approach was downscale based on the population. So the more the population a country has, the more share in the global planetary boundary it will get. Let me just quickly.
Maybe I should ask more precisely. How did you translate it then in square kilometers?
So we've got a global boundary value, right? And we've got uncertainties attached to it, right? So, and we have countries' population as well. So using arithmetic, mathematical operations, we did that.
So it was a
linearly divided planetary boundary. And this is for consumption-based. For production-based, it's based on biophysical limits, and in that we use potentially available croplands in the country using remote sensing techniques that are already available in the literature and the results that are already there. Yeah.
Okay. Any further questions?
Yeah.
And also we take this too.
Thank you very much for your presentation. Very interesting. I would have a question regarding the communication of your results, because I assume that you have an audience where you want to, like the audience that should take the numbers serious and delineate probably policy recommendation based on your accounts. And I would be interested in what are your thoughts, which number we should now provide policymakers?
So as I said, that this is undergoing a study. The manuscript is still in preparation, and we'll be taking part in a lot of interesting discussions about the results, and we'll be looking at the results in different perspectives. Yeah. So probably like watch out for this paper anytime soon.
Okay, so then I will rather comment than ask. I would say, depending on which of these indicators you use, you would have different target audiences. As was explained, allocating responsibility can be done differently, whether you think that the consumption end is responsible for the resource use or whether you think it's more at the production end, also has implications for whom you address with your messages. And probably you should not do one, you should do both. You should look at both ends and find your policy audiences at both ends. It's probably a safe bet to try and improve at all ends along these chains of supply.
Thanks very much.
So thank you very much for your presentation and the discussion. So we proceed with the next speaker, Maike from Stockholm Environmental Institute in Sweden.
Thank you. Good afternoon. My name is Mike Lathuillière. I'm from the Stockholm Environment Institute, and I'm going to talk about SDG 12. And before doing so, I'd like to acknowledge the co-authors, Javier Godard, Pernilla Löfgren, Ben Eyre, Toby Gardner, and Clément Suave. So as you all know, land plays a key role in Sustainable Development Goals. We've heard about this all week. These are two of the goals that I've isolated, and I tend to connect to these images on the right. But I would also argue that land could also be included in SDG 12, which is responsible consumption and production. And I'm really interested in these sub-goals that are shown on the screen. Achieve the sustainable management and efficient use of natural resources, which is 12.2, and 12.6, which is to encourage companies to adopt sustainable practices and to integrate sustainability information into their reporting cycle. But the image that we can connect to this goal is a bit less clear. But there's a useful framework, which we heard a little bit about in the previous presentation, which is life cycle thinking. Basically, the way that we look at the entire life cycle of a product, in this case, an agri-food product, starting from resource extraction and production through packaging and distribution all the way to the end of life of the product or even recycling. And over this life cycle thinking, we can do a life cycle assessment of a product that's a little bit more complex than a commodity, let's say a soybean. We could look at soy milk, because I tend to drink a lot of soy milk, but you can think of soy burger or maybe even feed if you're interested in animal production. So from this life cycle thinking, we do a life cycle assessment through product system modeling, following these very well established ISO standards that typically aggregate these impacts into these three main categories: impacts to natural resources, ecosystems quality, human health, from which we can improve the product system, but through which we can also communicate information. So if we think of soybean being produced in Brazil, that information could inform company or association sustainability policy. Or if we're thinking on the consumer side, let's say in Europe, that could inform the single market for green products, such as the recommendations for PEF, which is product environmental footprint, or organization environmental footprint guidelines. To carry out this work, we need to rely on data that are typically housed in these databases, such as EcoInvent, which would be the Swiss database. And the question is, how do we include land in this entire process, for instance, 1 kilogram of soybean, so that we can actually include it in these assessments, because it currently isn't systematically included. So very quickly, how does life cycle assessment work? Well, it works through 4-phase process. The first one being a life cycle inventory, where you make a list basically of the resources being used into your processes and your emissions. Those values get multiplied by impact factors, which are specific to the inventory results. That's the life cycle impact assessment phase. And the results, which are aggregated here into these 3 categories, then get interpreted. And the impacts are typically communicated per functional unit, for instance, 1 ton of soy. So what does this look like for land? Because this is fairly recent. Well, the life cycle inventory is the area occupied. That's fairly simple to understand, because we're interested in actually the impacts of land use change. These are the current models that exist, that have been developed and summarized in this paper by Kullner et al. In 2013. We have these impacts to ecosystem services, which are really the changes in the biophysical state of the land following land use change, and we also have biodiversity due to the loss of species following land use change. And those can get aggregated into ecosystems quality impact. Now, going back to this calculation, currently the issue is as follows. There's a mismatch basically between the impact factors, which are spatially explicit, linked to typically biomes or river basins if you're interested in water as well. Whereas the life cycle inventory information is typically aggregated at the jurisdictional level or the field level, for instance. And so if we're interested in finding out what the impact of this liter of soy milk is in Europe, knowing that the soybean that has been used to go into that product came from Brazil, we don't really have the proper matching between the two to be able to calculate that with great precision, or accuracy, I should say. Especially if we're interested in countries, and especially if we're also interested in traders. So this is really the goal of this research, is to accurately inform these life cycle inventories of agricultural commodities for consuming countries and traders, using trade information and land use information. And for that, we use the Transparency for Sustainable Economies platform, or TRACE, which has been introduced already several times in this conference. And then we combine that in the case study to provide an impact, biodiversity impact of 1 ton of Brazilian soybean exported to several countries and by several traders that appear in the TRACE platform. So very quickly, what is TRACE? TRACE combines export information, tax and logistic information to link Brazilian municipalities to consuming countries and to actors as well. And from that information, we basically extract the life cycle inventory that we need aggregated at the biome level. So we combine country and trader specific life cycle inventory information to then match with the impact factors that are available from Chaudhary et al., which turns out to be the recommendation from the UN Environment Life Cycle Initiative for these types of life cycle assessments. This is what the platform looks like if you focus on France. So you can see that we can link the flows of soybean. Here they're shown in tons, all the way to their source biome. So Cerrado, Atlantic, Cerrado or Savannah, which is this area, Atlantic forest, which is down here, Amazonia, and Pampa. Also, we have this unknown biome, which is really a part of the supply chain that we can't really resolve, so we don't really have a source biome for that particular country. We have the actors that are involved in the trade of this soybean, and these are also the ports, if you're interested in that. But we basically reorganize this information into the life cycle inventory, which is described here in square meters per ton, into their different biomes. So you can see that, for instance, Germany has about 70% of its soy being sourced from the Cerrado and the rest from the Amazon, whereas Finland is actually about close to 50-50 between Atlantic forest and Cerrado. The black is this unknown biome, which we show here as being an average Brazilian soy being exported from Brazil. If we apply the impact factor of biodiversity to this information, we then see the resolve and the difference in impact of that 1 ton of soy going to these different countries. And we see that Germany actually has the lowest impact. These impacts are in PDF, which is potentially disappeared fraction of species, which is typically used in LCA, but you can just do a relative comparison here to see the differences. And you can see also that the average value, which would be this average impact factor for Brazil, has this much greater impact, meaning that if we could resolve the biomes, we can actually get a much better differentiation between the exported soy. We can also do this for traders, which are ADM here, Bunge, Cargill, and Louis Dreyfus, showing roughly the same type of sourcing, except for Louis Dreyfus shown here as importing a little bit more from the Atlantic forest. biome, and then we can also apply the impact factor in similar ways to show the resolve here with a little bit of unknown biomes, which we're working on to reduce and be able to resolve this even further. So in conclusion, we find that trade information from TRACE can really improve the results of these product life cycle assessments, especially those including land use and LCA, although we could expand this method to other types of life cycle inventory, which could be based on river basins or fertilizer application, anything really, as long as we can match it to an importing country. The next steps is to expand what I've just shown to different countries and biomes for other countries, Paraguay, Argentina, and Bolivia, and to make this data available to the life cycle assessment community from our website, and also apply this method to more complex LCAs. So we really want to get to the veggie burger that would use soy, or to the feed, to see how that would be helpful. Once again, I thank you for your attention. I thank the team and the funders for this work. Thank you very much.
Michael, I think what came out very clearly is that such life cycle analysis can help trace back the drivers of observed land use change. Yeah?
Yes, as well. The drivers, perhaps not in a life cycle assessment per se, because we are thinking in terms of ton of product in this case. So really, what I see as I would see the most valuable result out of this research is to really be able to match the impact factor, which is available at many resolutions because it's based on biophysical information, to the particular biomes or the particular use of product that would go into the production of this commodity.
You or me? Okay. So any question, please?
Yeah, that was really interesting. Thank you. I'm not sure if you explained this and I missed it, but in terms of the trade links, and how do you resolve that across the supply chain as well of a product like, say, I mean, I guess with the land use, it's all happening really at the mode of production, but you said you could do other environmental extensions there. If you're looking at a complex product,
yeah,
how would you resolve those really complex trade links along the whole supply chain of the product?
Yeah, so we're really only focused on the commodity at this point. So we're taking the soybean and trying to trace it back to where it was produced. But you're right. I mean, if we're talking about soy milk, we'd have to understand where the cardboard came from, where the plastic covering came from, and this is where we hope to be able to work with perhaps a company that has better visibility on the sourcing of those other products, but perhaps not on the sourcing of the soybean, to be able to get the full life cycle. But you're right, as we would have to get more information on how the particular company making that product is sourcing those resources. Trace is focused mostly on agricultural commodities right now. So we wouldn't have that information at this point.
Well, thank you very much.
Thank you.
Then I would like to introduce the next presenter, Luigi, also from Stockholm, but from the Resilience Center. Welcome.
Hi everyone, I'm going to start because I only have 3 minutes. And as you can see, I tried to condensate the whole presentation in the title. And it's very long, but it has everything in it. So I'm trying to explore a different approach to quantify global scale the potential of water harvesting to increase crop production based on local case studies or local evidences, and with a social ecological perspective. We do this because we usually have very local, accurate case studies telling, the complex social ecological situation in the field, and also global estimates that are based on biophysical models that tell us what's the maximum optimal yield achievable under some ideal conditions. So I wanted to try to find a different way of having a global estimate that can rely on case studies. So we selected 171 case studies from the WOCAT dataset of water harvesting, defining water harvesting in a general way as all the practices that collect water from rainfall and runoff to be used in agriculture to increase soil moisture. So you can see like big or small ponds in field, swales, but also terraces. And every case study comes with an impact assessment where the farmers basically say how much the crop production has increased after the implementation of the practice. So the assumption behind this project is that when you have a certain increase in crop production at a local scale, you can expect the same increase everywhere in the world in agricultural land that have similar social ecological conditions. And to define the social ecological conditions, we selected 10 indicators regarding climate, like precipitation, seasonality, or land, like crop yield gap or farm size, and socio-economic parameters like access to market or financial services. And we used the 171 case studies with the 10 indicators to cluster the case studies in similar groups. So we came up with 8 social ecological groups of water harvesting. So basically with these 8 groups of water harvesting, we can in 8 groups represent the social ecological conditions in the 171 case studies. So basically the social ecological conditions are defined by the ranges of the indicators that you can see, and some are stand out for very high aridity, or like with specific socio-economic conditions, like very high financial access to financial services. So to outscale this at a global scale, we basically, going back to the assumption, we say if we have a grid cell, every pixel in the grid cell that has social ecological conditions within the ranges defined by one of these 8 clusters, then it belongs to that cluster. By doing so, we came up with a map covering roughly 19% of the global agricultural land, which basically means that with 171 case studies, we can cover the social ecological conditions in the 19% of the global agricultural land. And we use these maps, as you can see, there are different groups in different areas of the world. And we use these maps to outscale the impact assessment within the case studies and say if in the region you have 10 case studies saying that the cropping production could increase by 50%, that means that the whole region you can expect the same increase in crop production. So we came up with a final map showing where in the world you can expect an increase in crop production based on similarity in social ecological conditions. I was very quick, so if you have any questions, just ask me. Thanks. Yeah.
Okay, a short question. Is there a short question and a short answer, please?
Yeah.
Murray Scown from Utrecht University. My question is, why could you only get 19% of the cropland? Is that a data availability limitation in terms of attributing grid cells with all these different factors?
Yes, it is. It's related to the case studies. So the maps that we have at the end basically tells that that the social ecological conditions captured by the 171 case studies, you can find the same conditions in 19% of the global agricultural land. So if we had 500 case studies covering more areas, you might expect to represent a higher percentage of the agricultural land, basically. Yeah. Thank you.
So the next speaker is Michel from Prixi, Italy. Michel?
Thank you. Hello, everybody. Yes, my name is Daniele Ehrlich. I'm the last on the list of the authors of this paper. I understand I have 3 minutes, right? Yes, more or less, yeah? Okay. So, and this is about monitoring and measuring SDGs. Just wanted to say that it is based on a global map of built-up areas. Before we have heard about forests produced by Hansen from the Landsat data, we have done the same for urban areas from 75 to now, and which is the map that you see in the background. We have done it in 4 slices, 75, 90, 2000, 2015. And we use it for a number of applications, but today I talk about SDGs because I only have 3 minutes. So, and all the information you can get from this website, what I'm saying now, and all the data also, yeah? So, we start from, as I say, from the built-up map. So we have 4 slices, and they are then gridded at 250 meters. So we call them spatial grids of built-up. But then we have also produced spatial grid of population density, together with season in New York, Columbia University in New York, which is this. And the 2 data layers, 4 slices each, match perfectly. And this is a unique data set to monitor SDGs. And I'll tell you which ones we are monitoring now. So first of all, I give you an example of, oops. Yeah. So what you can get out of this data set. So I just took 2 cities random, and you can see the expansion of built-up from red, which is 75, into 2015, which is the yellow. And this is for 2 areas of the world, but you have this for the entire world. So if you're interested, you can get that. And of course, you can get here, this is Ho Chi Minh, this is Chicago. And then if you have also the population like we have, you can know how much is the built-up area and how much is the population. And you can see there are striking differences, and so also striking land use efficiency differences. So this is the data sets what we are using, and this is, I want just to make sure that you understand that these data sets are available, and there are not so many data sets you can, like this, that you can use for monitoring sustainable development indicators. So which ones are those? So first is the degraded land. I shortened the title. You can read the full goal. And here we are measuring the proportion of land that is degraded over the total. And this is basically we are measuring change of built up. Now the important thing is that we are continuing to produce data layers into the future with the same methodology. So the information are homogeneous and comparable in time and in space. Just to say that from 1990 to 2015, 250,000 square kilometers were added, which is the equivalent of the country of Romania or the state of Oregon if you are from the United States. So it's a huge amount. And this will be added the next 30 years again. And we heard before that out of every percentage of built up, you get 12% impact on all the land uses. So this is for the, and then the second indicator, which we are perfectly on target with this data, is the ratio of land consumption to population growth. And this is 11.3.1. And just wanted to say that this is a ratio, so we need to have both the changes in built up and the changes in population. So, and we are able to measure this with this indicator, yeah. And just to say that there is difficult to compare the 2 indicators, the 15.3.1 and this one, because this is a ratio. So it captures both the population and the built up. And let's say that you have 10 people, 10 units, 10 people and over 1 hectare growth in the first case, and 100 people and 10 units in the second case, the ratio is the same, but the amount of built-up that is actually consumed is 9 times as much. So there are issues between the compatibility of sustainable development indicators within that frame. And just to say also that we have produced this land use efficiency indicator for the entire globe, for this 10,000 over city centers that are processed through a set of thresholds of population built up to come up with urban and rural area. But I'm not able to tell you more because time is running out. I just want to tell you that some of the work is on indicators, for example, for 11.1 is described in a paper. Most of the description of the data sets that I have described you now are available from atlases they have produced, and of course, from the research papers that underpin this. And all this information is available on our website. So please, if you would like to use the data, test the data, or get the publication, or get the tools, we have produced also a land use efficiency tool that you can take our data and actually calculate it for your own areas. You go there and you get it, and you can download it. So with that, I conclude my presentation because I think the time is out. Yep.
Okay, thank you. One question? That's not bad. So we come to the last presentation, last but not least presentation for today. Tamara, University College Dublin.
Hi, yes, I'm Tamara Hochstrasser from University College Dublin, and I would like to give you a small introduction to a research project that I conducted for the Irish Environmental Protection Agency. Ireland, 30% of the greenhouse gas emissions, the national greenhouse gas emissions in Ireland come from agriculture because the agriculture is mostly livestock based. It is very difficult to cut these emissions, and actually the only way to cut those emissions is to cut the national herd. But of course this is undesirable because Irish agriculture is providing a lot of employment opportunities that are extremely important to continue the viability of the rural environment. So for this reason, I conducted this scoping project where I was trying to find out what would be alternative land use types that would maintain agricultural output while also addressing sustainability goals like carbon neutrality. And my first step in this was to look at drivers of land use and response variables in land use. Similar to very many researchers in this conference, and I basically saw it in every talk, I conceptualized the external world as a system and that is explored by a learning cycle. Hay et al., which are referenced there in the Journal of Environmental Management, they have formalized this approach, and I thought it was important to communicate this conceptual approach to my stakeholders so they could understand why I want to research the goals, the activities, and the system elements for this scoping project. The system elements I scoped by doing expert interviews. The experts that I interviewed were selected for their holistic approach to Irish land use and their experience with stakeholders. I asked them to provide a narrative on past land use change, on the future that they were envisioning, and if they thought that something in the land use legislation, in the land use policy, needed to be changed. this is the results I got. And basically what I did is I extracted from the narrative that they provided the system elements that, that were mentioned in the interviews. This is organized by the spatial, these are system elements that are spatially variable, so like GIS layers, okay? According to the sustainability concepts, the three spheres, environment, social, and economic. If you want to know more about this project, you can read the report. It's now published, or email me. You can see it there as well. Actually, I did this work for the EPA because I wanted to make sure that all the sectors are considered in trying to envision this land use transformation in Ireland. Another initiative that I have done just recently, and this is launched now just 2 weeks ago, is a web page where practitioners and researchers can exchange research ideas, and I'm hoping that this will also help to integrate between the sectors. Thank you for your attention.
Thank you, Tamara, for your nice presentation and for keeping time very well, which is a key challenge for 3 minutes talk. Thanks. Is there a question? Okay. Yeah.
Email me if you have questions.
You received a lot of emails. So Holger is going to summarize what we have here today in the afternoon session only, or on the afternoon session, and then we continue in a discussion where we stay with the methods available and where could we go, where what could be improvements. Okay.
Thanks. Just 1 minute on 3 hours, so to speak. Morning and afternoon should be seen as one continuum, I think. So the question was really, how to meet sustainably the different demands on land. Sustainably within the SDGs and within the planetary boundaries. And we heard a lot about these different demands relating to food, which was a large factor, to climate protection, to protecting biodiversity and ecosystems, but also a number of other outcomes were mentioned, not the least those that refer beyond food to other livelihood components and human well-being. What indicators do we have? What do we want to observe and do we want to operationalize and use? Clearly, the planetary boundaries is one set of them. The SDG indicators that we saw is another set of them, but there are others that we need to take into account to be able to quantify and measure eventually. What's the role of science, of land system science in all this? And what are the methods and tools that are in use? We saw quite a number of them, and from the set that we already had in the morning, models, scenarios, data analysis, case studies. There were additional ones coming in this afternoon, in particular those that relate to trade, which seems to be one important leverage, one intervention, which can either help or not help to come to more sustainable land use. But there are others again. So we would like to make this a package of what are these issues, what are the potential ways forward, pathways, solutions, interventions, what is the role of science, what kind of methods and tools does science have. So that's our offer, so to speak, which we like to take forward beyond today in various ways. One of them may be a paper, one of them may be a special issue, other workshops and other formats that we propose, and we invite you all to be part of that. But right now we'd like to get your feedback on what you heard, either from the morning or from the afternoon. We only have 10 minutes, but if you wish, we can probably go a little beyond that. Benjamin, do you want to take again the role, or should I? Well, just get started. Just get started with questions or comments. Yes.
I have a suggestion, maybe both as an indicator and as a narrative. I really like it's for maybe related to SDG 12 that we have said of sustainable consumption and production. I really liked how Mohammad, you were looking both at actually this is the consumption and the production at the same time, because I think in many studies it's only the one side which really puts a lot of bias on the results and the narrative which comes out of it. And my suggestion to go further is actually, let's imagine that you're invited at a party and you're asked to bring your own food. Well, on the one hand, you wouldn't consume, so eat more than you have brought, and on the other hand, you wouldn't bring more than you need, that you would eat. If you translate this in land, it means that we might want to have as well the crossing effects, that you don't want to consume more that you are able, so your embodied consumption should not be more than your land is able to produce, and you should not produce more than your population needs. This is more a national perspective, and it's not good to answer all the questions because it really raises issues of well, fairness and equity, because highly densely populated countries will be not favored by this narrative, but I think it's still an important narrative and indicator to look at.
Thank you very much. Some countries might be quite shocked with this perspective. If you look, for example, at the Middle Eastern countries, they might not like that. But of course, it's a one starting point that can help you to get towards sustainability. What other perspectives or questions or issues would you like to raise?
Thank you. I'd like to raise the idea of, I was just rereading the title of the session here, and thinking about relative versus absolute sustainability. So planetary boundaries is more in absolute terms, and LCA, which I was showing, is more in relative terms, where you say that one product is better than another, and so on. And I think it's important to really be careful when we talk about sustainability, and whether we're talking in terms of relative terms or absolute terms, because that will help at least with the language and what we're talking about. Often you hear, you know, such product or such diet is better than another, but if everyone adopts that one diet, maybe it's not good anymore. So things like that sometimes could skew some of the potential solutions.
Thanks very much. Maybe you also think about where you would like to see the whole GLP community moving. What are the issues that GLP should address, that land system science should address, that are maybe not covered enough yet, in order to move towards this broader view of meeting all the demands sustainably? Any suggestions or other questions? Well, otherwise we simply leave it at that. I just wanted to give you a chance to comment if you wish.
Yeah, just a short one that relates to the presentation that we've seen in the afternoon. And what I really liked about that is that different groups looked at different compartments. And especially, again, if you look at the discussion on also what you refer to, what is a planetary boundary really? So where's the biophysical limit that we don't want to touch to make something sustainable or not? I think we had the urban. This is part of it, and often neglected in the GLP community here, so it belongs to that. Also because it's related to agricultural land that is eaten up by urban. That's only part of the story, but it is an important part. And then we have the deforestation part of that directly relates to the climate change way of looking onto planetary boundaries. I think all of these three compounds, let's say, belong to one storyline, and if you really want to make it a sustainable land systems perspective, systemic, then you need to into account all three of those. Otherwise, you lose it. And if you want to link that then back to the SDGs, it becomes even more important to do so, because if you only focus agriculture, or only focus deforestation, or only focus urban expansion, you always lose some of the 169 SDG indicators, or however you term it, if you want to quantify it.
And if there's no other comment, I might just give a short response to that, which is, yes, indeed, you want to take a systemic view, and that may also be one of the big tasks for science, not only to address it in its analysis, but also to eventually communicate that complexity in ways that help decision and policy making. Big challenge, but something that certainly is on or should be on the agenda of GLP and of scientists in general. If there's nothing more, there doesn't seem to be, then this is really almost the closure of today. There's one more session, the plenary session, which starts in, I think, 15 minutes over in the main building. Thank you very much for showing up in such a big numbers and morning and afternoon session. We much appreciate that, and have a safe trip back. Thank you.